Hello, welcome back everyone. This video is about information from section 1.2 of AP Calculus, defining limits and using limit notation. So what we're going to do in this video is look at what a limit is and how limits are written and do a few examples. Should be a fairly short video, or at least hopefully a lesson in which we can do the lesson in one video. So here we go. First, the definition of a limit. What is a limit? So given a function f, so let's call this function right here f of x that I've drawn. The limit of f of x as x approaches c is a real number r if f of x can be made arbitrarily close to r by taking x sufficiently close to c, but not equal to c. So let's see what's happening here. What we have here is we have some value c. And we're going to let our x values get closer and closer to c. Okay? Now, if you look at our picture here, you know, when the y value is right about here, or pardon me, when the x value is right about there, the y value over here is right around here. And what happens is, as x moves closer to c from that direction, the y value is going to move up in that direction. And the same thing happens from the other side. As the x value moves closer and closer to c, the y value is going to move closer and closer to this other value. And the actual value that it ends up taking in this, and this one's a simply laid out one, is this is our r value that the function is getting closer and closer to as x gets closer and closer to c. Now, this, of course, is a function where the limit and the value of the function end up being the same as each other, which makes this a little bit, less important for us. But, suppose that there was a hole here in this graph at x equals c, we would be concerning ourselves not with what the value of the function was there, but with what the value of f of x was approaching as x was approaching c. And as we go on in future lessons, at the beginning of this unit, you will see more and more this idea about, what is the function getting closer to as the x value or the independent variable approaches a particular value. So let's talk about notation. This is the standard notation that you see right here for writing a limit. Typically, I pronounce this the limit as x approaches a of f of x equals r. So I tend to use this as my pronunciation. But the notation that we've written there can be said in a number of ways. It could be said the limit of f of x as x approaches a equals r, or we could say as x approaches a, the limit of f of x equals r. Those are all fundamentally the same verbal way to say what this limit notation is saying. The limit as x approaches a of f of x equals r. Okay, go ahead and pause the video for a few moments and try your hand at example 1a and b and see how you do answering those questions. Okay, I'll be back with you in a few seconds after you unpause. All right, I'm back. So let's look at example 1. Rewrite the limit from symbolic to verbal or vice versa. A function f of x is modeling behavior around the value x equals 2. It is found that limit as x approaches 2 of f of x is equal to 11. Notice how I even read it that way. I read it the way I'm going to write it. Write this limit as a sentence. And so you could have had any one of 3 possible answers. Like I said, I normally use that top one. This says the limit as x approaches 2 of f of x equals 11. You could also have written the limit of f of x as x approaches 2 equals 11, or you could have said as x approaches 2, the limit of f of x equals r. All right, and then part B, it is found that g of t can be made arbitrarily close to 15 by making t arbitrarily close to -3. Write this relationship with a mathematical statement. So what we have here is we have g of t is getting closer to 15, while t is getting closer to -3. So what we're talking about here, we're talking about the limit as the variable approaches a value, and we're told that t is getting arbitrarily close to -3. The function that we're taking the limit of is this function right here, g of t. And that value, the limit, is getting arbitrarily close to 15. And so this is how we would write that English statement in mathematical notation. All right, let's go on to the next page for a few more example questions. Start here with example 2. From the graph of s of x shown, what do you suspect is the value of the limit as x approaches 3 of s of x? So the first thing I do is I identify where 3 is on this graph. Right there is where 3 is. So what this question is asking is, as x gets closer and closer to 3, what value is y getting closer and closer to? And for years I've kind of counseled my students on how to handle finding a limit on a graph like this. As you know, imagine yourself actually standing on and walking on the graph. What happens, let's start over here to the right of 3, maybe over here at 4. What happens to the y value as we start here and we walk along that graph and get closer and closer to where x is equal to 3? Same thing, what happens as we walk across the graph from this side as x gets closer and closer to 3? And from both sides we approach this value right here. And it looks like that value is about 1.5. And so we're going to say that the limit as x approaches 3 of s of x is equal to 1.5. We will go into a great deal more detail in a later lesson when we talk about how to find limits graphically. We'll do a bunch more examples like this, and you'll see some other nuances that you need to consider when you're finding a limit graphically. All right, let's look at example 3. From the table of values of q of t shown, which of the following is the most likely value of limit as t approaches 2 of q of t? Now I'm going to pause for a second and talk about why it says most likely instead of just saying which of the following is the value of the limit as t approaches 2 of q of t. When we're looking at a table of values, we're never quite 100% sure that the limit is what it appears to be based off of the table of values. And again, we'll talk about this more when we talk about finding limits from tables. But when we create a table for an equation, as long as we choose good t values as we approach the value we're looking at, our table will actually tell us, give us enough information in those situations. But when we're just looking at a table that we didn't generate, we're not necessarily sure. For instance, if I put another t value in here for t equals 1.999 or t equals 1.9999, this graph could, behave very unpredictably as we approach 2. And so I'm not 100% sure. But looking at this, the most likely, let's go to most likely, as we get closer and closer to 2 from each side, what number does it appear that q of t is getting closer and closer to? And it looks to me like that value is -3.5. So I'm going to go ahead and select -3.5 as my answer there. Again, we're not 100% sure that that's the limit from this table, but it is definitely the most likely limit based off of the information that we see in this table. All right, last example. Example 4, it is found that as x approaches pi, corresponding values of a function L of x approach the value e. Which of the following is an equivalent statement? So x approaches pi. So we're looking for, the limit as x approaches pi of something. So that enables me to eliminate a bunch of these. I can eliminate this one, L of x gets closer to pi. That's not even a valid notation, nor is the notation in part B. In part C, we're finding the limit as x approaches e, so that's not what we're looking for. D is a limit as x approaches pi, so that might be our answer. E and F, again, we've got x approaching c instead of pi. In G, we've got a limit as x approaches pi, and at H, we've got a limit as x approaches e, so we can eliminate that one. So we've narrowed it down to 2 just by using the concept of the limit as x approaches pi. All right, our function that goes in our notation is L of x, and the value that it approaches is e. And so that's what it's equal to. So this is what we're looking for. And notice the difference between choice D and choice E. Choice D says the limit as x approaches pi of L of x, whereas choice G says the limit as x approaches pi of L of e. Okay, this is the actual function that we're looking for, and so D is going to end up being our answer choice. And that takes us to the conclusion of this video. For those of you who are in my class, notice the assignment at the bottom. Go ahead and complete that before we see you again next time. All right, I'll see you next time with a video from Section 1, Unit 1, Section 3. Okay, have a great rest of your day.